Good morning, all, and thank you for being here. Today, we'll be speaking about the implementation of Lakeflow Connect at EFSA. EFSA is the European Food Safety Authority in Europe. This is the agenda of the session. I will give you an introduction and a few words about my organization, and then I will give the floor to my colleagues from Delaware, a company helping my organization in the implementation, our partner, and they will go into the technical details of the topic. So I'm Giancarlo Costa from EFSA. I'm Cloud Solution Architect there, and I'm here with Tim and Jeroen from Delaware, as I already said. Few figures about EFSA. EFSA was founded in 2002, and we are about 600 staff, and we focus on scientific risk assessment in Europe, and we do this through the help of several hundreds of scientific experts that are collaborating with us for the production of the scientific opinion that we use as output for our assessments. We run several meetings and produced several tons of opinions since the foundation. We are part of the network of agencies in EU focusing on One Health, like the Chemical Agency in Finland, the ECDC Agency on Human Diseases in Sweden, the Environmental Agency in Denmark, and the Medicine One in Holland. As I said, we focus on risk assessment, which is producing independent scientific advice, enforce the communication among the European institutions, promoting the scientific operation, but we do not do risk management. Risk management, it is in the end of the Commission, of the Parliament, and of the national authorities in the member states. How do we work? Basically, the Commission, the Parliament, the member states, or even EFSA itself, in case we see the urgency of studying a topic, we get a mandate, okay? And we execute the mandate with the help of a panel of experts and a scientific working group to produce our scientific assessment. What do we use? We use, for sure, people, as I said. We use science, all the available scientific literature. We use protocols, and more and more we use data and AI because we are an evidence-based organization. Basically in 2019, we started the migration of our architecture to the cloud, and we decided to adopt several cloud platforms like Appian, tools from the Commission, Salesforce, okay, and we integrated them in Azure using almost real-time event integration for process integration. And for a while, we continued that way, but we discovered that, relying only on events makes then the data and analytics job of the data science not really solid. And this is why, when we heard about Lakeflow Connect, we really started experimenting with it because we wanted to have on our, let's say, integration cloud, which is Azure, reliable data for our data scientists. Basically, now today we speak about Lakeflow Connect for Salesforce, which I believe one of the first one, which went GA in March. And in Salesforce, basically, we have all our processes that are engaging the external stakeholders. And this is an example of the open public consultation that we run in Europe with the citizens when we have a new topic, we are working on it. This is also to increase the transparency of our work. And the Salesforce data are brought now to our integration cloud for data analysts using Lakeflow Connect. I will now give the floor to Tim, and he will start going into the technical details. Thank you.
Okay, I'd like to walk you through how we built EFSA's new central data platform from the ground up using the medallion architecture. When we kicked off this project in 2020, our biggest advantage was starting with a blank slate. We weren't tied to any existing data warehouse or legacy platform. We agreed with each of our data producers on some things up front, the format they sent the data to us, how often they sent the data to us, and the path they used to send it. On the other side, our consumers were the open EFSA portal and a suite of downstream APIs. Their needs defined our performance and data quality targets. To ingest data, we supported both batch loads and near real-time streams. We used Azure Event Hubs for streaming, but quickly discovered that it became more micro-batch processing. And next to this, we also used Azure Data Factory for orchestrating the Databricks jobs. Once the data arrived, it landed in our landing zone, and from there we applied incremental cleansing and conformance in the middle layer. Then it was called the canonical data model. Before producing our final tables, we then called the views, analytics-ready, business-curated data sets, and finally those tables were published to a SQL database that powers the Open EFSA portal and the API services. So the medallion structure we are now using everywhere at EFSA follows the raw prepare serve instead of bronze, silver, gold, but what's in a name? Let me walk you through how EFSA's raw prepare serve pipeline works using a simple Lego analogy. First, imagine every data producer handing us boxes of loose Lego blocks in our raw zone, and we keep those blocks sorted by source. Just like shelving separate bins for source 1, source 2, so on, and this gives us a clear, untouched record of exactly what arrived from which provider. Next comes the prepare phase, where we start organizing the pieces more meaningfully. Legos can be sorted by colors, size, or at EFSA, the function, and we merge and structure the data across providers, more around the dossiers, the questions or organizations, and this is where the raw pieces take shape into coherent sets that share a common context. Finally, in the surf layer, we transform those organized sets into polished sculptures. Ready for use, think of a completed Lego model with every block in place, delivered to our data consumers, where it's a dashboard, an API, the Open EFSA portal, and they get a fully assembled product they can trust and build on. Now, let's zoom in on how this looks in practice. We start at the left with our third-party systems. We have Appian, ESFC, Oracle, Eka, Salesforce, each sending data into our integration layer through API management. As each payload arrives, we first do an envelope check to confirm it's well-formed JSON. Valid messages are then forwarded to a payload check, where we verify if they adhere to our agreed schema and business rules. And once the message passes both checks, it lands in the event hub for downstream processing, and it's also stored in an archive on a data storage. Not every source uses real-time APIs. For example, Oracle HCM exports comes as CSV dumps at an adjustment we made when we encountered reliability issues with the live feed. Regardless of how data arrives, our Databricks pipelines pick it up, transform according to the prepare logic, and then load the final result in 2 serving layers. In short, producers feed data, envelope payload validation, event hub ingestion or CSV import, Databricks processing, and then to the final layers. Over time, we ran into bottlenecks with Event Hub. Its retention window gave some issues, and it kept messages at 1 megabyte. And some events and dossiers became larger and larger, 10 megabytes, and we needed to find another way to work with it. We started first with base64 encoding, but yeah, it became a hassle. And then Databricks released Autoloader, and we saw an opportunity to simplify and harden our pipeline. Since every incoming payload was already being written to our storage account for archiving, switching to Autoloader required almost no rework. And we simply stopped forwarding data to the event hub after the payload check, and instead, autoloader picked it up from the storage account. Today, our flow is even leaner. Data arrives, envelope payload validation, file lands in the storage account, autoloader picks it up and processes it. By removing event hub from the path, we reduced some points of failure and improved end-to-end reliability. We noticed during the process that our Lego analogy didn't cover all tracks we were walking, so let me shift gears a bit and share a new analogy we're using, a restaurant. Imagine our data producers are the ingredient suppliers, and their raw ingredients arrive in our storeroom where we sort and organize everything by type, by freshness. And next, our data chefs take over, transforming those ingredients into distinct offerings. A buffet-style walking dinner. Here, consumers like Power BI users can browse an array of prepared components and serve themselves whatever they need. Flexible on-demand access to pieces they want. Plated dishes, the other one. For services like EFSA, we deliver fully completed dishes, complete polished data sets ready to consume without any additional assembly. This restaurant model highlights how we go from raw inputs to both modular building blocks and finished meals, ensuring every data consumer gets exactly the experience they need. But even though our event-driven architecture ticked a lot of boxes, like Giancarlo said, we began to uncover its limitations in practice. First, unanticipated edge cases kept popping up, scenarios our initial flows didn't capture, forcing us to revisit and rework pipelines on every site just to plug the gaps. At the same time, we saw data drift, network hiccups, misalignments meant some events simply never arrived, leaving holes in our event stream. And while we built a sophisticated logic to handle the SCD2 data, it wasn't foolproof. Data producers sometimes strayed from our naming conventions, so key fields in events weren't always consistent. In short, missing edge cases coverage, transmission gaps, and inconsistent schemas highlighted the need for a more resilient approach, and that was fulfilled by Lakeflow Connect, which my colleague will explain.
Thank you, Tim. In the new architecture, we implemented Lakeflow Connect to ingest Salesforce data as part of our transition away from a complex event-driven architecture. For EFSA, it was mainly important that the data is reliable so that it can also be used for analytics. It's also important that the history of the data is preserved, and more specific, in a SCD2 format. SCD2 is a strategy to manage changes in data over time. Each record has a start date and end date to specify from when to when the data is valid. When the data is updated, a new record is inserted and the old one is preserved. In the old record, the end date receives the timestamp of change, which is the same value as the start date of the new record. In the new record, the end date is not yet specified, and this also specifies that the data is still valid. And this will allow us to build a complete history of the data over time. Salesforce only offers limited support for history tracking, so the new solution has to handle this constraint. For the new solution, we compared 3 possible solutions. The first one is Lakeflow Connect. This is a connector offered by Databricks, and it's built on the DLT framework, so it's actually a pre-built DLT pipeline. The second possible solution is Salesforce Bulk API with Azure Data Factory. This is also a connector and uses a snapshot approach. Lastly, we have the old solution, which is Salesforce Event Change Data Capture, in which we use the Azure Event Hub and a Event Hub connector to transform the events to tables on the Delta Lake. As you can see, Lakeflow Connect is the best fit for EFSA. It supports incremental load of the data, which allows for a minimal achievable latency of only a couple of minutes. It's also easy to implement and easy to maintain, which also makes it a robust solution for the future. SD2 is not yet supported out of the box, but it's easy to implement because Lakeflow Connect has as output streaming tables, So you can use the DLT framework to build a DLT pipeline for streaming processing so that you can add SD2 to the tables. In the first run, Lakeflow Connect will ingest all the data, and as from the second run, it will use a reference column to check which data has already been ingested. And it sees which data has been changed and will only ingest those. For example, a reference column can be the last modified date or a system mod stamp. Lakeflow Connect is also completely serverless, so you don't have to manage a complex infrastructure by yourself. It's also multi-cloud supported and natively integrates with Unity Catalog, which allows for governance. Lakeflow Connect exists for Salesforce, but also for other data sources. For example, SQL Server, which is also on the roadmap to be implemented at EFSA. Lakeflow Connect situates itself in the ingest layer. And more specific, it's of the type streaming. For the implementation of Lakeflow Connect, we used 3 key components, namely Databricks as the central data platform, in which we use Lakeflow Connect as connector to ingest the Salesforce data, and also to do the data manipulations, for example, adding the SD2 logic. Secondly, we used Microsoft Azure as a cloud platform for the infrastructure hosting. And lastly, we also used Terraform to deploy the resources. This allows us to create a cloud-agnostic solution to be more future-proof. In Databricks, we have built a workflow that consists of 3 stages. The first stage is that we ingest the Salesforce data with Lakeflow Connect, which is a pre-built DLT pipeline, so it's a pipeline task. Secondly, we use the streaming tables to apply through a DLT pipeline in which we use streaming processing to add the SD2 logic. And lastly, we can also serve the data downstream. So we are now going to show an example of how you can implement Lakeflow Connect in Databricks. So in Databricks, we created 3 new resources, namely 2 pipelines and 1 Databricks job. The first pipeline is a pipeline that will be automatically created once you configure Lakeflow Connect through the Lakeflow Connect UI. Secondly, we also have the pipeline to apply the SD2 logic. Lastly, we have the Databricks job, and we use both pipelines. The Databricks job is completely serverless and scheduled to run once per day. When we go to the first task of the pipeline, we have Lakeflow Connect to ingest the Salesforce data. We can go to the Lakeflow Connect UI, and there you can specify the Salesforce connection that you want to use. Based on the Salesforce connection, you can see which objects you can ingest, and you can select those that you want. You can also specify the destination that you want to use for the tables in Unity Catalog. Lastly, you also have the option to specify if you want to receive any notifications if the pipeline succeeds or fails. And you can also add the schedule to the pipeline. Lakeflow Connect underlyingly creates a view that contains the incremental load of the changed data. Optionally, it also creates a second view if we have on Salesforce side formula fields in the table. Then it will also take a full snapshot of those. Then both views will be combined through a join, and the output will be a streaming table. You can also see this visualized. In the second task, we will apply the SD2 logic to the streaming tables. When we go to the settings of the DLT pipeline, you can see that it's also completely serverless and that it has a triggered pipeline mode because it will start when the first pipeline of Lakeflow Connect is finished. We also defined a source notebook in which we have the source code for the DLT logic. When we go to the source code, you can see that we will create a list with all the tables that we have in the landing zone, and we will iterate over the tables. For each table, we create a DLT view to have the incremental changes of the data, and then we will write those away to a streaming table. We also use a reference column for example, the last modified state to define based on which the ST2 has to be built up. Lastly, you can also add a third task to serve the tables downstream. Now we are also going to give an example in which you can see the ST2 logic in Databricks. So for example, EFSA has an account that is called Delaware. And they want to update Delaware to Delaware Consulting to make it more specific. So they go to Salesforce and they update the account name. And then when the Databricks job is triggered and when it has completed, the changes will also be reflected in Databricks. So you can see a new record is inserted with the updated account name, and the old record is preserved. The old record, its end date, is a timestamp of change, and in the new record, the start date has the same value. You can also see in the new record that the end date is not yet defined because the data is still valid. Lastly, we also used Terraform to deploy the resources in Databricks. Terraform is a tool that is used for infrastructure as code that you can use to create and manage resources through APIs. When you work with Terraform, those APIs are abstracted away. Typically, a Terraform workflow consists of 3 stages. First, you have the Terraform write, in which you define the infrastructure in a configuration file. Secondly, we have the Terraform plan, in which we compare the new infrastructure to the current one, and then you can see if you want to apply those changes. If you agree with the Terraform plan, so if you agree with the changes that will be made to your infrastructure, you can also do the Terraform apply, in which the infrastructure will be provisioned. At EFSA, we already used Terraform to manage the infrastructure. So we only had to create 3 new resources, namely the 2 pipelines, the Lakeflow Connect pipeline and the ST2 pipeline, and also the Databricks job. So we are now going to give an example of how you can implement Lakeflow Connect through Terraform. So first, we have the Terraform write stage. We have 2 configuration files. So one configuration file for the pipelines. There we have the Lakeflow Connect pipeline and the ST2 pipeline. And we also have the jobs configuration file, in which we have the Databricks job that consumes both pipelines. First, we go to the pipeline configuration file. On this slide, you can see the Lakeflow Connect pipeline reflected as a Terraform resource. You can also define the Salesforce connection like we do in the Lakeflow Connect UI, also the destination in the catalog, and the objects that you want to ingest. Secondly, we also have the ST2 pipeline, and you can also see the path reflected to the source code notebook with the ST2 logic. Lastly, we have the jobs configuration file, in which we have the new Databricks job. You can also see in the tasks, in the first 2, that the Lakeflow Connect pipeline and the ST2 pipeline are reflected. You can also define the schedule that you want to use for the pipeline, and, for example, also if you want to receive any notifications if the Databricks job succeeds or fails. Secondly, we have the Terraform plan. At EFSA, we use Azure DevOps pipelines to deploy resources, to deploy the workflows across the different environments. We also integrate Terraform in those pipelines. In this example, you can see the Terraform plan. The Terraform plan shows that a new pipeline will be created. In this example, it's the Lakeflow Connect pipeline. If we agree with the Terraform plan, so if we agree with the changes that will be made to the infrastructure, we can also do the Terraform apply. Terraform apply will provision the infrastructure, so the resources will be created in Databricks. So this was our presentation. Thank you for coming to our session.